Hello, my name is Esther Fraser, and today I'm going to talk to you about Analytic Tableaux as a proof system for first-order logic. First, I'll define Tableaux and show you how to construct them. We'll run through two examples, and I'll introduce a unifying notation that'll make them even simpler. Then, we'll show that Tableaux are a sound and complete way to produce proofs in first-order logic. The proof of soundness is fairly straightforward. Completeness is a little bit trickier. First, we'll talk about Hintika's lemma. We'll show a systematic way for constructing Tableaux, and we'll put those two things together for a proof of completeness of Tableaux. The proofs I'll present follow very closely the proofs in Raymond Smullyan's book First Order Logic. I used the 1995 Dover edition. First, some preliminary notation and definitions. To cut down on the number of parentheses we have to parse through, I let p juxtaposed with x represent some statement possibly containing the variable x. And I'll use p juxtaposed with k to indicate the statement p in which every instance of x has been replaced by k. This is the usual notion of variable substitution. I've just taken out some of the parentheses because it's easier to see. Now, because we're dealing in first-order logic, we need a universe U of individuals, some non-empty set, and we use EU to denote the set of all closed U formulas. Now, because it's going to come up a lot, I'll remind you of the definition of a first-order valuation. So V is a first-order valuation of EU if it's a Boolean valuation, that is, it preserves the normal truth table ideas of and, or, not, and implication, with the additional two properties that the statement for all x, p of x, is true under V if for every element k of our universe U, p of k is true under V, and the statement there exists an x such that p of x is true under V if and only if for at least one element k of U, p of k is true under V. We are now ready to define Tableaux. Let x be a formula. An analytic tableau for x is an ordered dyadic tree whose points are formulas. X is at its root. The remainder of the tableau is constructed by successive application of the following rules. We have rules for each of the connectors and their negation, as well as rules for the universal quantifier and its negation, and the existential quantifier and its negation. So if a node is of the form not x, its immediate successor is x. If a node is of the form x and y, its immediate successor is x and it has further successor y. If a node is of the form not x and y, the tableau branches into left successor not x and right successor not y. A node of the form x or y also branches, with x as its left successor and y as its right successor. Not x or y has immediate successor not x and further successor not y. Implication x implies y branches into not x on the left and y on the right. And the negation of implication, not x implies y, has immediate successor x and further successor not y. These rules are sufficient to deal with propositional logic. For first-order logic, we also need rules for dealing with quantified statements. For all x, p of x is succeeded by p of a, where a is any variable. The negation, not for all x, p of x, is succeeded by not p of a, provided that a is fresh. By fresh, we either mean brand new or any variable that has not been assigned other properties. The important thing, just like it is in natural deduction, is that when we pick an A to say this is the A for which not P of A, we haven't already given that A some other property in, for example, there exists an X such that P of X, because we can't actually back that up. All we know about this particular A is not P. Similarly, for the existential quantifier, there exists x p of x has to be succeeded by a fresh a in p of a. This is really similar to our for all introduction and existential elimination in natural deduction. It's there for the same reason and it provides the same certainty. And our very last rule is the negation of the existential quantifier. Not there exists x p of x is succeeded by not p of a, where a, again, is any variable. A few more words that we use about Tableau. We say a branch theta of a tableau is closed when that branch contains both a formula and its negation. A tableau itself is closed when all of its branches are closed. And a closed tableau for not x constitutes a proof for x. In this way, all proofs by Tableau are really proofs by contradiction. They rest on the assumption that for any x, x or not x is true. Before we go any further, let's do an example. Suppose we want to prove the statement, there exists an x such that p of x and q of x implies there exists an x such that p of x and there exists an x such that q of x. To start the tableau, line 1, we write the negation of that statement. From our negation implication rule, rule 4b, we immediately have there exists an x, p of x and q of x, and following that, not there exists an x, p of x, and there exists an x, q of x. That uses up line 1. For our own bookkeeping purposes, we can put a check mark next to it so that when we're scanning back up our tree for unused lines, we know we don't have to look at that one. Now we look at line 2. There exists an x such that p of x and q of x. By using our existence rule, we pick a brand new a to substitute into our statement and get p of a and q of a. That uses up line 2. Line 3 is of the form not and. We know that a not and branches. We could do that right now, but it is always more efficient to defer branching to the last possible moment so that we don't have to write the same statements in each of our branches. We can put them further up in the tree so that they're involved in all of the branches after the split as well. So let's skip line 3 for now. Line 4, p of a and q of a, we use our and rule to immediately get line 5, p of a, and line 6, q of a. This uses line 4. Now, there's no deferring it any longer because lines 5 and 6 are both atomic. There's nothing we can do with them. Our tree must branch. To the left, we have not there exists an x, p of x. That's our not and rule applied to line 3. Now, in not there exists, we can pick any variable we like, and because we are halfway intelligent people, we see that if we pick a, we will immediately get a contradiction. So we pick not p of a, that spends line 7, and we have a contradiction between line 5 and line 8. This closes the left half of this closes the left branch, and we scan back up the tree to see what else is unused. We still haven't spent line 3. It branches to the right, not there exists an x, q of x. This spends line 3, and again, we judiciously select not q of a. This spends line 9, and we have our contradiction between line 6 and line 10. Now the right branch is closed, all branches of our tree are closed, and we have a proof for our original statement. Let's do one more example. Suppose we want to prove the statement, for all x p of x or for all x q of x implies for all x p of x or q of x. Again, we start with the negation as the root. From our not implies rule, we immediately have the antecedent and the negation of the consequent. Now that spends line 1. Line 2 is of the form or, that's a branch, so we'll defer it for now. Line 3, not for all x. Our not for all rule, we need to select a brand new fresh variable. We'll pick a, since we haven't used anything yet. That spends line 3. From line 4, not or, we have not p of a and not q of a. That uses up line 4. Now there's no delaying it any further. The only non-atomic formula we have here is line 2 with its branching or. On the left side, we have for all x p of x. With a for all statement, we can pick any variable we like. We might as well pick a to get our contradiction. That spends line 7. And 5 and 8 form a contradiction, closing our left branch. Our right branch begins with for all x q of x. That uses up line 2. Again, we pick q of a, using up line 9, and we derive a contradiction from lines 6 and 10. Now, intuitively, the formulas from example 1 and example 2 are kind of dual to each other. One has existential quantifiers where the other has universal. One has and statements where the other has or statements. The antecedent of one kind of looks like the consequent of the other. And the proofs bear that out. They have the same number of lines, the contradictions come from the same places, and you feel like you're sort of doing the same thing. But the rules in the right-hand side are totally different. We use 4b at the beginning, sure, but we have a 5b where we had a 6a, we have a 3b where we had a 2a. The proofs themselves aren't using the same rules. But the similarity of structure suggests an underlying similarity. To formalize this symmetry, Smullyan introduces a unifying notation. He recognizes 4 types of formulas: conjunctions, disjunctions, universal statements, and existential statements. And he groups all of our other rules into these 4 types. So the first is type alpha, or conjunctions. These are formulas that are true if 2 related formulas are both true. So that's our normal use of the word conjunction, x or y, which is true if and only if x is true and y is true. But it's also true for the negation of a regular type disjunction, not x or y, which is true if and only if not x is true and not y is true. This, of course, is one of De Morgan's laws, the equivalence between not x and y and not x and not y. And Smullyan here just kind of goes with that. We also know that that's true about the negation of an implication, which is true if and only if x is true and not y is true. We see that equivalence in truth tables all the time, and it's a shortcut that we use as mathematicians in mathematical proofs. And if we allow the 2 related formula to be identical, we see that not x is also a type of conjunction, true if and only if x is true and x is true. So those are the 4 types of conjunctive statements that we have, and they're all grouped together under type alpha. The second type is disjunction, formulas that are true if and only if at least one of 2 related formulas is true. So that's the regular disjunction, x or y, true if and only if x is true or y is true. But it's also one of the other laws of De Morgan, the negation of a conjunction, not x and y is true, if and only if not x is true or not y is true. It's also true for an implication, which is true if not x is true or y is true. And Smullyan also includes not x again here, true if and only if x is true or x is true. The reason he does this is because it leads to some pleasing symmetric properties for conjunctions, disjunctions, and negations. That's outside the scope of this presentation, but you can read more about it in his book. So conjunctions and disjunctions take care of the rules for propositional logic. For first order logic, we also need to deal with quantifiers. There are two types of quantified statements. Universal statements, type gamma, are formulas that are true if and only if a related formula is true for every member of a universe. So that's the regular universal quantifier for all x p of x, which is true if and only if p of a is true for every a in U. And it's also true about the negation of the existential quantifier. Not there exists x p of x is true if and only if not p of a is true for every a in U. The last type of statement is an existentially quantified one, type delta. These are formulas that are true if and only if a related formula is true for at least one member of U. So that's the regular existential quantifier. There exists an x such that p of x, which is true if and only if p of a is true for at least one a in U. And it's also true of the negation of the universal quantifier. Not for all x p of x is true if and only if not p of a is true for all a in U. And this is the type of statement that requires a fresh variable for exactly the same reasons as we needed freshness in natural deduction. So you'll note that these related statements are either the immediate subformula or the negation of a subformula. With that categorization, we can now restate our Tableau construction rules, bringing them from 6 two-part rules down to 4 one-part rules. We have rule A to deal with alpha statements. A node alpha is succeeded immediately by alpha 1 and then by alpha 2. Rule B deals with beta statements. A beta is succeeded on the left by beta 1 and on the right by beta 2. Rule C deals with gamma statements. Gamma of x is succeeded by gamma of a, where a is any variable. And rule D for existential statements. Delta of x is succeeded by delta of a, where a is fresh. Now that we have that idea of categorization, we can make more precise our idea of the similarity or symmetry between our two examples. So what we have here are the formation trees for the two formulas we were looking to prove. Example 1 on the left and example 2 on the right. The idea of a formation tree is to break a formula down into its component subformulas. So you have the formula at the top, the immediate subformulas right underneath, and so on and so on. So that sense we had that the formulas were kind of the same is really a product of the fact that they were both alpha statements, each composed of a delta and a beta. The delta was itself composed of an alpha statement, the beta of 2 gammas. The only difference between them really is that in example 1, the antecedent of the implication is the delta statement, whereas in example 2, the delta statement was the consequent. So they're composed of formulas of the same type in almost the same order. And that similarity is borne out in the proofs. While the proofs used rules of different numbers, under our unifying notation, they use exactly the same rules. First rule A, then rule D, rule A again, rule B, and rule C. The only difference is whether rule B is applied to line 3 or line 2, and that just stems from the fact that in one example, the beta statement is alpha 1, and in the other, the beta statement is alpha 2. Now that we've seen how to construct Tableaux, we're ready to figure out if they actually work. For our proof of soundness, we need two quick definitions. First, a Tableau T2 is an immediate extension of a Tableau T1 if it is the result of applying one of rule A, B, C, or D to one of the branches of T1. So it's an extension because it's T1 plus a little bit more, and it's an immediate extension because it's only a very little bit more. Second, a branch theta of a Tableau T is called true under evaluation V if every term of theta is true under V. The Tableau T as a whole is true under V if at least one branch of T is true under V. Now we're ready to sketch the proof of soundness. Every formula provable by Tableau is true. Essentially what we're going to do is show that an immediate extension of any true Tableau T is also true. There are only 4 ways to extend a Tableau, so there are only 4 cases we have to check there. Then by induction on the size of T, any Tableau with a true origin is true. A closed Tableau cannot be true under any interpretation, therefore, because a closed Tableau, by definition, contains a contradiction. The origin of a closed Tableau must then be unsatisfiable, and so every formula provable by Tableau is true. We won't do all the cases in the proof of soundness in detail because they're all pretty straightforward. We'll just do rule D because that's the most interesting. Let T be a true Tableau. Then T has at least one true branch. Call that branch theta. Let TD be an immediate extension of T created by applying rule D to some branch theta prime. If theta prime is distinct from theta, then TD still contains the true branch theta, so TD is still true. Now if theta prime is identical with theta, that is, if theta was extended by applying rule D, then the branch theta contains some delta type formula, call it delta x, and was extended to include delta A, where A is a brand new variable. Since delta x appears in theta, delta x is true. By the definition of a first order valuation, there's at least one element of U for which delta is true. Since the variable A has not yet been used, we can use it here to designate that element. So delta A is true, so the extended theta is true. So TD still contains a true branch, so TD is true. So in the case of a branch being extended by rule D, we preserve the trueness of the Tableau. And the cases for rules A, B, and C are very similar, even simpler. So we know that everything we prove by Tableau is true. What about the completeness of Tableau as a proof system? Is it the case that everything that is true is provable by Tableau? The good news is yes, but it will take us a little bit of work to get there. In order to prove completeness, first we're going to introduce the notion of a Hintika set, named after Jaakko Hintika, the mathematician who first studied them in detail. We'll show how systematization can deal with infinite branches of our Tableau to ensure that they are Hintika sets. We'll then show all Hintika sets are satisfiable, and then we'll put all of those pieces together for a sketch of the proof of completeness of first order Tableau. First things first, Hintika sets. A Hintika set for a universe U is a set S of U formulas such that the following conditions hold. First, no atomic element of EU and its negation are both in S. Second, if alpha is in S, then both alpha 1 and alpha 2 are in S. Third, if beta is in S, then either beta 1 or beta 2 is in S. Fourth, if gamma is in S, then for every element k of U, our universe, gamma of k is in S. And if delta is in S, then for at least one element k of U, delta k is in S. So we can think of this informally as being a set that contains a node in a proof and all of the successors of that node. Now, in propositional logic, or in finite universes, all tableaux are finite. But in an infinite universe, it's possible, even easy, to create tableaux which have infinite branches that aren't Hintika sets. For example, if we construct a tableau by selecting a formula of minimal level and appending all of its related formulas immediately, we would get stuck adding gamma of A, gamma of B, gamma of C, gamma of D, the very first time we encountered a gamma formula. And since U is infinite, we'd neglect everything else in the tableau, trying to add all of the members of U. So the key is to find a systematic procedure for constructing tableaux so that all of the open branches are necessarily Hintika sequences. There are lots of different ways to do this. This is, I think, the easiest to justify, and it's the one that Smullyan presents in his book, although there are many, many others. So we begin the tableau with the formula whose satisfiability is being tested at the origin. That's step 0. Now suppose we've completed the nth step. If the tableau is closed, we stop. Alternatively, if every non-atomic point on every open branch has been used, we stop. Otherwise, we find an unused point x of minimal level, which appears on an open branch. If we want to be completely deterministic about it, we can pick the leftmost branch. This is why we specified that the tree has to be ordered in the first place. That way we can avoid trying to invoke the axiom of choice, and we can make this algorithm completely deterministic. We extend the tableau by taking every open branch theta, which passes through x, and extending the branch according to x's type. If x is an alpha, extend theta to theta alpha 1 alpha 2. If x is a beta, extend theta to 2 branches simultaneously, theta beta 1 on the left and theta beta 2 on the right. If x is a gamma, take the first parameter a such that gamma of a does not occur on theta, and extend theta to theta gamma of a gamma. And we'll talk about that more in a moment. Lastly, if x is a delta, take the first parameter a, which does not appear on the tree, and extend theta to theta delta of a. After extending theta according to x's type, we declare x to be used, and step n+1 is now complete. So let's talk a little bit more in depth about case 3. If x is of type gamma, we not only add gamma of a, but we also repeat an instance of gamma. This is to avoid that infinite gamma loop that we were talking about earlier. By appending just one of the gamma k's and adding another gamma, that allows us to move on, but come back to that gamma and adjoin the next one. So by adding the successors one at a time, we'll be sure to fulfill that gamma formula, but without neglecting the alpha, beta, delta, or other gamma formulas elsewhere on the tree. We can think of this process as constructing the tableau breadth-wise rather than depth-wise. However, because of this gamma repetition, these tableaux are not, technically speaking, analytic tableaux. Call them rather systematic tableaux. But it's pretty easy to see that by deleting these gamma repetitions from a systematic tableau, we can easily obtain an analytic tableau without losing out on anything important. This is clear if you consider any example of a tableau closed after arbitrary repetitions of gamma or gamma k's. If the tableau could close at, say, gamma of D, we didn't have to do gamma of A, gamma of B, or gamma of C. We can take them out. We can take out the other gammas, no problem. Before we get to Hintika's lemma, we need a few words on finished systematic tableau. A systematic tableau is called finished if either it is finite or if it cannot be extended by the systematic procedure. A finished systematic tableau may well have infinite branches. However, if the tableau is being constructed by the procedure we've just outlined, each of its open branches will be a Hintika sequence. It's also possible for the tableau to have a finite open branch on which every non-atomic point is used. This could occur if the branch has no gamma-type formulas, or if the quantifier of the gamma formula is vacuous, such as in the statement, for all x, 3 is less than 4. Well, that statement's the same whether x equals 1, x equals 2, or x equals 10 billion. So that quantifier doesn't make a difference to this statement. Now we're ready to show Hintika's lemma. Hintika's lemma for first-order logic states that every Hintika set S for a domain U is first-order satisfiable in U. And the way the proof works is roughly like this. We want to find a first-order valuation in which every element X of S is true. We start with V, an atomic valuation of EU, which we define by saying every atomic element of S is true, anything else is false. By induction on the degree of X, we can extend that valuation to all of S and show that every X in S is true. Our base case is quite simple. If X is of degree 0, it's true from the way we defined V. Right? X of degree 0 means that X is atomic, so it's true. Now, say that X is of degree n, and let all elements of S of degree less than n be true under V. Again, we have 4 cases to consider, whether X is an alpha, beta, gamma, or delta. But in each case, the truth of X relies on the truth of formulas of lesser degree. And in each case, those formulas of lesser degree are going to be in S because S is a Hintika set. So in the alpha case, alpha is true if and only if alpha 1 and alpha 2 are both true. Because S is a Hintika set, alpha 1 and alpha 2 are in S. Alpha 1 and alpha 2 are each of degree less than alpha, because alpha is of degree of alpha 1 plus the degree of alpha 2 plus 1. So they're in S, they're of lesser degree and they're true, so alpha is also true. The case for beta, gamma, and delta is similar. So in each case, X is going to be true, regardless of its type. So for every element of S, of any degree, that element will be true. Completeness for first-order Tableau is in sight. We have 2 quick stepping stones to gather together this information, and then the proof will be a piece of cake. The first is the result that for any finished systematic tableau, every open branch is a Hintika sequence for a denumerable universe of parameters. That's just from the way we constructed the systematic procedure. Pretty easy to see that if we do things the way we outlined, we'll fulfill all of the formulas. We're not going to get stuck in any gamma loops. There's no other real trouble spots to be worried about. And the denumerability condition just follows from the fact that we have to actually be able to enumerate the gamma case. Our second result is that for any finished systematic tableau, every open branch is simultaneously satisfiable. This comes from the result we have above. All of our open branches are Hintika sequences, and Hintika's lemma, which we just outlined, that any Hintika sequence is simultaneously satisfiable. So with that hop and that skip, we are ready to jump into completeness. If X is valid, then X is provable. That is, if X is valid, there exists a closed tableau for not X. Here's how the proof goes. Suppose that X is valid. Let T be the finished systematic tableau starting with not X. If T contains an open branch, theta, then theta is satisfiable. but then not x, which is a term of theta, would be satisfiable. And that's in contradiction to the hypothesis that x is valid. Hence, T contains no open branches, so T is closed, so T constitutes a proof for x. That's all there is to it. Note, we can actually say something a little bit stronger. By Koenig's lemma, which states that every finitely generated tree with infinitely many points must contain at least one infinite branch, every closed tableau is finite. So in fact, if x is valid, the systematic tableau for not x will close after finitely many steps. Now, that doesn't always give us practical information, because 10 billion steps is a finite number of steps, but not always an easy number of steps to execute. So, we've done some Tableaux. We've shown that Tableaux in general are a sound and complete way to construct proofs. What makes them particularly appealing is that they lend themselves really well to mechanization. So I think the visual structure of the Tableau really suggests that unifying notation of alpha, beta, gamma, and delta. It really lays things out in a way that illuminates the underlying symmetry of a lot of these formulas. And that unified notation reduces the amount of work required for any proof relying on the degree of a formula, like completeness did, or the length of a proof. That unified notation also makes it easier to design systematic ways to construct Tableau, because any system only has to handle 4 cases of formula, and every formula can be decomposed into subformulas of 4 types. So there's just a lot less work to do to classify the formulas. We're only sorting them into alphas, betas, gammas, and deltas, and not ands, ors, nots, negations of ands, negations of implications, for all statements, not there exist statements. We only have 4 types to worry about. And because they lend themselves this well to systemization, Tableaux lend themselves really well to mechanized proof search. Much easier to have a lookup table to say, okay, what kind of formula is this? That funnels everything into just 4 categories. So that concludes my remarks for today about Analytic Tableaux. For more on Tableau and automated proof search, you can read Melvin Fitting's First Order Logic and Automated Theorem Proving, published by Springer in 1996. A lot of work has been done in the intervening 20 years, but I think Fitting's book is really good for an introduction to how that works. Much of the information I presented today comes directly from Raymond Smullyan's First Order Logic. I use the 1995 Dover edition. Here are the page numbers in there for some of the things that I touched on today that we didn't get to explore more in depth. And he also has a chapter on Tableau versus Gensen systems, their equivalents, a little bit on block Tableau, and the similarities there. That's in chapter 11. This concludes my presentation. Thanks very much for your attention.